Hi, and welcome back to another video in our Chapter 9 series. In this video, we're going to talk about how do we find what's called the radius of a convergence. Sometimes we interchange the word radius of convergence with interval of convergence, and they're very similar. And we'll talk about the distinction here, but for our intent and purpose, we're going to be looking for what we are going to refer to as maybe the beginnings of our interval of convergence. So we have a series here, and if ever our series is geometric, then we treat that interval of convergence just like we would for any geometric series. We find our multiplier, our R value, that common ratio, and we say that the common ratio, the absolute value, has to be greater than 1, resulting in an inequality where we have our R value placed between -1 and 1, and then we solve for x and we get our little interval of convergence. Now, the interesting thing about a geometric series is that at the endpoints, the series will never converge. And so you will find that every geometric series has an interval of convergence where the endpoints are not included. Here we have an example of a series that at first glance might appear geometric, but because we have this n multiplied right there, this is not a geometric series. This is just a generic type of series. And so to find the interval of convergence, what we're going to use is we're going to consider a test that we learned back in the first part of chapter 9 when we were testing for convergence, and that test is the ratio test. Now, the ratio test is kind of like a cousin to a geometric series. In a geometric series, we're going off the principle that we have this R value, this multiplier, that we multiply by a constant thing to get the next term. Well, here with the ratio test, what we're doing is we're saying, well, if we were going to consider having a multiplier, we know that this is not a geometric series. However, if the ratio between the terms is approaching a certain type of value, then we can say that it has a behavior similar to a convergent geometric series. So they're related, but not quite the same. So let's talk about how we're going to approach this. Basically, I'm going to take this. This is called my nth term. So I'm going to call this an. And if you remember what our ratio test does, is it says if I take the limit as n approaches infinity of an plus 1 over an, basically what's going to happen is I'm going to get one of three results. If I get a limit that's equal to 1, back in our series situation, we said that, well, if the limit is 1, we call that an inconclusive result, and we would have to go on and try a different type of test to see if our series converges. But in this series, remember, we don't know what this series is. We have an x, we have an unknown variable. And so what we're doing is we're trying to find all the x's that would create a convergent series. So we then would look for, okay, if L is less than 1, then I know my series converges. If L is greater than 1, then my series diverges. So basically, I want to focus in on this result of L being less than 1. And so what I want to do is I want to solve for all the x's that would create a limit where I get a value less than 1. Okay, so that's kind of where I'm going for. So I'm going to set up my limit. So as n approaches infinity, I'm going to show my ratio. And what I'm going to do is when I do this, because x could be a positive or a negative number, I don't know what kind of a series I'm going to get. Sometimes I'll get an alternating series. Sometimes I'll get all positive terms. The whole goal here, though, is to figure out what values of x give me a limit with a value that is less than 1. So what I'm going to do is I am going to take the absolute value of the series. And what that's going to do is it's going to let me find the values of x that 100% for sure my series will absolutely converge. That means it'll converge whether it alternates or whether all the terms are positive. So in every circumstance, I'm going to find first the interval of x's that will always produce an absolutely convergent series. So I'm going to throw absolute value bars around this, and I'm going to set up my ratio. So I'm going to have n plus 1, x to the n plus 1, and then I'm going to have 10 to the n plus 1, divided by the original nth term. Now, when I simplify this, I'm going to take that bottom fraction and I'm going to flip it. Multiply by that reciprocal. Kind of get rid of that there. And so now I am ready to simplify. And so as I simplify, here's what I want to do, and here's the approach that I want to take. I want to gather all the things that don't cancel out. And so as I'm looking at this, I see x to the n plus 1. I'm going to rewrite it as x to the n times x to the 1. And then 10 to the n plus 1, I can also write as 10 to the n times 10 to the 1. And by splitting up my exponent, now I can cancel that x to the n. I can cancel the 10 to the n. And my result is going to look like this. It's going to be the limit as n approaches infinity. I'm going to gather first all the remaining n terms. So I have an n plus 1 in the numerator, and then I have an n in the denominator. And then what's left, all the numbers and any x terms, I want to kind of separate those and create two separate fractions that are multiplied together, or two separate factors that are being multiplied. And you'll understand why here in just a minute. But I have an x left and a 10. And so this is kind of the result that I have right now. Now I'm going to remember that when I'm evaluating limits, I can separate my limits and consider my limits of each multiplied value separately. So what I'm doing is I'm breaking this up. And this first value, n plus 1 over n, I'm going to have infinity over infinity, which we know is an indeterminate form. And I'm not going to write that on my paper, but mentally I'm going to recognize that that's what's going to happen. And so I've got two ways to deal with that. I can use L'Hopital's rule and do the derivative of the top over the derivative of the bottom, or I can use an end behavior model. What I am not doing is canceling. I am not canceling things. You cannot cancel these n's. Please don't do bad algebra here. Whenever you have an n plus 1, if two terms are attached with an addition or subtraction sign, we like to say they're married for life. You can't break them up. So don't bust that relationship up. But what we can do is we can consider the n behavior model of n over n. And so whatever the n behavior model is approaching as n approaches infinity, well, that's going to be the limit. And so this limit is going to be 1. Now, the second limit is simply going to be the absolute value of x over 10, because there is no n to consider there. And you can kind of think of that as an independent constant. So if you remember when we had the limit as n, approached infinity of like 5, and we said, oh, the limit of a constant is just a constant. It's kind of that same thing. X and 10 are not related to n. And so the limit as n goes to infinity is simply going to remain x, the absolute value of x over 10. Now that we've simplified our ratio test, let's go back to the whole goal here. We said in the beginning that in our ratio test, we were focusing in on trying to get a limit where the value of L, the result in our ratio test, was less than 1. So once I simplify and I have all the n terms kind of limit out and figure out what those limits are, I see that I have x over 10. And so now what I'm going to do is I'm going to say, well, this, in order to converge, has to be less than 1. And from this point forward, it's going to feel like a geometric series with our approach, because we're going to take this little statement here and we're going to evaluate that. And we're going to say, well, x over 10 has to be less than 1 and greater than negative 1. And then we're going to solve our inequality. Negative 10 is less than x, which is less than 10. And so we get this little interval of convergence, which I hesitate to call this our interval of convergence, and we'll talk about that why, but we kind of have our initial interval. And the title of this video is the radius of convergence. Well, if our series is centered at 0, and we can see that our series is centered at 0 because we have x and not like x plus 1 or x minus 5 or something like that. I also know that I'm centered at 0 because if I were to take this little interval and make a little number line and go from 10 to negative 10, 0 would be right smack dab in the middle. And so whatever the value is directly in between the two endpoints of our interval, that is going to be the center of our series. So there's a couple different ways to figure that out. And you guys, the radius of our series is exactly what it sounds like. It's the distance from the center to the edge of the interval. So here my radius of convergence is simply 10. So the radius of a convergence is a number that measures from the center out. So what is basically the length of the interval, and then it goes from the center to the endpoints, and it should be the same because the center is the center and it's symmetric. So it's half the width of the interval is another way to think about it. Also, if you subtract your endpoints and divide by 2, so the right endpoint, which is 10, minus the left endpoint, which is negative 10 divided by 2, that will also tell you your radius of convergence. So there's a formula if you like to use formulas. But that's how we're going to approach finding the radius of convergence. Now, what that will do is it will say that, hey, anywhere, any x value that I choose between 10 and negative 10 is going to produce a series that when I run the limit comparison test, a direct comparison test, the ratio test, or any of those tests that I've ran, the integral test, any of those convergence tests will give me a result saying that that series converges. Now, the trouble with these non-geometric series is that while we can start out using the ratio test to find an initial interval, the difference here is when we do the ratio test, where a geometric test, a series will diverge when r is 1. Let's recall that in the ratio test, when we got L equals 1, that was considered an inconclusive result. And so what happens is at the endpoints, at 10 and negative 10, if we were to do the ratio test, we would get a result of exactly 1, meaning that we don't know what's happening at the endpoints. It is not a guaranteed divergence like we have in a geometric series. And so at that point, what we need to do is we need to take some steps to test those endpoints. And that's going to be what we cover in the next video in the series. So here in this video, our goal is simply to talk about what is our radius of convergence and how do we get that initial interval. So to find out what happens at our endpoints, you're going to go and watch the next video in the series. Now, as we look at different series, we're going to find that different series will behave differently. So let's take a look at this series. We can see that it's not geometric. So we can't use our geometric series to find our interval or ratio or, sorry, radius of convergence. So what we're going to do is use that ratio test. So we're going to do the limit as n approaches infinity, and we are going to set up our ratio. So we're going to have the n plus 1 factorial x minus 4 to the n plus 1 all over n factorial x minus 4 to the n. And we're going to simplify. So I'm going to break up any exponents that I have. This is going to be x minus 4 to the n times x minus 4 to the 1, canceling away that x minus 4. And then here we've got n plus 1 factorial over n factorial. And I'm going to remember that n plus 1 factorial can be written as n plus 1 times n factorial. And if you need a little brief explanation as to why that works, go watch the video on the ratio test from the first part of chapter 9, and we'll kind of walk through that. But I can cancel out these, and so here's the result that I get. And it's a little bit different than the one we just saw, because it says n plus 1, and if I separate this like I said I would, I kind of get this result. Now, the limit as n approaches infinity of n plus 1 is infinite. So herein lies the problem. We don't have a situation where we have like infinity times infinity or infinity times 0. We have infinity times the limit of this expression is the absolute value of x minus 4. Now, remember that our ratio test requires that our result be less than 1. That is what we are looking for and trying to solve for. So what value of x would make a situation where we have less than 1? Well, there's only one possible value that would give us a result where our limit as n approaches infinity is going to be less than 1. And that is the value x equals 4. Only at x equals 4 will this be equal to 0. And I want to give a distinction here. We've already evaluated the limit. So I know we've talked about situations where we have an indeterminate form where we have like infinity minus infinity and infinity times infinity and stuff like that. Whenever you're worried about that, I want you to think to yourself, am I approaching a value? Am I approaching 0, or am I equal to 0? Because there's a difference. Here we are equal to 0. And so we have an infinite amount multiplied by an exact value of 0, not a value approaching 0. So we get indeterminate forms when we have values that are approaching 0. Here, there's no n that is approaching anything, so it's literally just x minus 4, and when x is 4, that value is equal to 0. So there's your little distinction. And so what we have here is we have a situation where this series will only converge for one value. So converges only when x equals 4. There's no interval, it's just a single point. And when x is 4, the series converges to 0. And so when we talk about what our radius of convergence is, if we converge at a single point, our radius of convergence will be 0. So different series have different behaviors. And so now we've seen two scenarios where we have an interval, and maybe the endpoints converge, maybe not. That's the next video. We've got a single point where our series converges. And there's one other series, one other scenario and situation that could happen. So let's take a look at that one. All right, here we have one last series to examine. And this series, we've written out a few of the terms, not a big deal. So whenever we're trying to find a radius or an interval upon which the series converges, we're just going to look at the nth term. We're not going to worry about the other terms. So I'm going to set up my ratio test, the limit as n approaches infinity, and I'll have 10x to the n plus 1 over n plus 1 factorial. And I know I'm going to divide by this fraction, so I'm going to just right off the bat go ahead and flip my fraction to the reciprocal. That's an okay thing to do. It's not a big deal if you do that. I'm going to split up my exponents, so I'll have 10x to the n and 10x to the 1. Replace that. And then n plus 1 times n factorial. And that'll allow me to go and cancel some things. So n factorial will cancel, 10x to the n will cancel, and so I get this situation. The limit as n goes to infinity is 10x. Well, I've got, let's see, what do I have left? 1 over n plus 1, and then 10x on top. And so as I split this up, I'll have the limit as n goes to infinity of 1 over n plus 1 times the limit as n goes to infinity of 10x. Now, on this one, you might notice that this limit of this first value is 0. The second value is simply just the absolute value 10x, which when I multiply those two together, I get a limit that is 0. Now, let's recall what we want to have happen here with the ratio test. We want to have a value that is less than 1 to show convergence, and 0 is in fact less than 1. So I know the series will converge based on this ratio test. So I know that that is the result, but let's think about the implications of what just happened. This series or this ratio test will give us a result of 0 no matter what I plug in for x. So if I kind of go back to this step right here and I plug something in for x, it doesn't matter what number I plug in for x. I could plug in 5, I could plug in 15, I could plug in 15,372,486. That series is going to converge because the ratio test produces a result of 0 every single time. And so when I have a situation here where my result is not dependent, so it does not depend on x, that means x can be anything. So that's what I want to kind of remember here, is that x can be anything. And so my interval of convergence is just all real numbers. And so usually we write it as interval notation, and that's going to be my interval of convergence. And so my radius of convergence is infinite. So if you wanted to write that, your radius is infinite. So yeah, we have 3 possible scenarios when we're looking at series and doing this ratio test. The first thing that can happen is we can get an interval where we have an endpoint, and then we'll have to test those endpoints. The second thing we could have is maybe we converge at a single point, and so that is often when our limit will only converge if x is a certain number, like on the last example, x had to be 4. And then the final result that we can have, the possible outcome, is that our series converges for all real numbers, and that happens when we get a result that does not depend on what x is. So sometimes maybe x will like cancel away. and there won't be any x's left. Or in this case, you'll have a limit that approaches 0, and it'll be a value less than 1 regardless of what x is. So you have to put a little bit of analytical thought into what you're seeing on your paper. But those are the 3 possible outcomes that you could have when you're doing the ratio test. So in summary, here's kind of what we just talked about. And if you want to pause the video and jot down any of these notes, feel free. But again, these are the 3 situations that we can come across when we're using the ratio test to find our interval or radius of convergence. And remember, the interval is an interval. The radius is a single number. So from the center to an endpoint, that will be the radius of convergence. So now you've got it. Go practice.